Hi everybody, I am on page 16, the graph of the derivative function. This is a really big, important topic. We're starting easy, and I'm going to try to explain this the best that I can as we go through. Okay, looking at number 1, I did find a new feature on here. Yes, it's like a laser pointer. Okay, so I now have a laser pointer, so I don't have to circle this 700 times. Y equals negative x squared plus 3. That's what's graphed here. It's the parabola. What I want you to do, well, we'll do this part together, is find the derivative of that. So here's the function. It's a pretty easy function to take the derivative of. I'm going to label it f prime of x, and you should have this done before I'm even getting there because I'm delaying a little bit. The derivative is negative 2x. Okay, from the power rule, that's what we get. Now, you're going to fill in the table. So take a second to fill in the table, plug negative 2 into there, and get your answer and fill in the table. I'm going to pause while I do that. You guys, pause this video and then do that. Okay, so my table is filled in from plugging those values into the derivative. I'm going to now answer the question, why does f prime of 0 make sense for this particular function? So let me change colors here. If I'm looking at the graph of the parabola that's graphed, I'm seeing the turning point at 0. So does it make sense that the derivative would be 0 there? Yeah, because the slope right there is definitely 0. If I draw on a tangent line, it's going to be horizontal. So the answer to B, why does f prime of 0 make sense for this particular function? I'm not going to write it out because you've seen my writing on this thing. I'm just going to say it. The derivative at the turning point must be 0 because it's a horizontal tangent. Okay, now I'm going to plot the points from the table, and this is going to be what the derivative looks like. Okay, so I'm going to make this a little bit bigger, and I'm going to plot the points from the table right now. Okay, first point, negative 2, 4. The next point, negative 1, 2. 0, 0, we talked about that one. 1, negative 2, 2, negative 4. Okay, so you can see that, hang on. Yes, it made a line. Okay, I'm not going to put arrows on that. You guys know that there's arrows on that. All right, here's why that picture makes sense. There's just a lot of reasons that go into why the derivative looks like the way it looks. First and foremost, the power rule. Think about what the power rule does. The power rule takes the exponent, the degree, and decreases it by 1. So the fact that I started with a parabola and my derivative is a line makes sense. Every single time we have a parabola, the derivative is going to be a line. Every single time we have a cubic, the derivative is going to be a parabola. It's going to go from a degree of 3 to a degree of 2. So there's the first very basic thing we have to recognize, that if you're given a picture of a bunch of functions and you got to match them up with the pictures of derivatives, that's one easy thing that can get you to sort of start matching them up correctly. Realizing that the derivative has to be 1 less degree. Okay, next thing, I'm going to get both of these in view here. Oh, that line doesn't travel with it. I forgot to group it. Okay, listen, I'm learning here, okay, people? All right, I can do this without seeing that whole parabola. If I think about the slopes that are on this portion, and I just highlighted up here, of the parabola, all of those slopes, when I go to draw in tangent lines, I'll kind of just try to draw one in right now. When I go to draw in a tangent line, let's say right there, going to have a positive slope. So that's why all of these outputs, aka y values, are positive. When we had a turning point, we had already talked about this, the slope is 0. When we have the parabola going down, all of those have negative slopes, negative sloping tangent lines. The slope at any of those points is negative. That's why all of these values are below the x-axis. And this is a thing I'm going to point out a lot. When the actual function right here is increasing, you're going to get positive slopes, positive numbers. So your derivative is above the x-axis. When you have something like a turning point, there are other ways this could happen, but if you have something like a turning point, the slope there is 0. So that's reflected on the graph of the derivative by hitting the x-axis. When your original function is decreasing, it's reflected in your graph of the derivative by being negative numbers, aka below the x-axis. Okay, I'm on number 2. If we're taking a look at the function right here, I want you to go ahead while I'm kind of delaying and use the power rule to state the derivative of that. Okay, that should have been enough time for you to use the power rule on that. I'm getting x squared plus 2x minus 3. There's the derivative. It should not be a surprise that that's a parabola. The original y that was given is a cubic. It has a degree of 3. And when we do the power rule, we know we go down a degree, so the derivative is an x squared, a quadratic. Okay, you guys are going to put this in your calculator. You can pause, go grab your calculator if you don't have it, and then go to the table, fill in the table, plot your points, and then come back and compare with mine. Okay, so there's the table, and there's my parabola. Now, the next question says, why does f of negative 2 make sense for this particular function? So for f of negative 2, they have negative 3, what we got. So if I go over to the function and I look at where negative 2 is, it's right there. Why does a negative derivative make sense? Because if I were to draw in a tangent line right there where you see the dot, it would have a negative slope. All of these guys, positive slopes. Here the slope is 0. All of these guys, negative slopes. Here the slope is 0. Then all these guys have a positive slope. So at negative 2, how do I know it has a negative slope? Because it's decreasing. It makes sense because f of x, regular f of x, is decreasing. That says because f of x is decreasing. Okay, so going through that again, let's just relate, I'm going to grab my highlighter again. Let's just relate the function that's graphed to the derivative that we just graphed. All of these slopes right here are positive. So all of these values are positive. All of these slopes right here are negative. So all of these slopes, numbers are negative. Those values are negative. The rest of the way, all of these have a positive slope. That's reflected in the derivative because the derivative is telling you the slope. It's giving you positive values. What's happening right here and right here? Well, I already talked about it. The slope is 0, so that's reflected in the graph by being at the y value of 0. If I look at this graph and think about what the slopes are, positive, then 0, then negative, then 0, then positive. That's reflected in here by the y values being positive, then 0, then negative, then 0, then positive. Okay. What I want you to do right now is pause the video and pick your choice for all of these, just based on what I was talking about in the last page. I want you to circle, like here's your function, f of x over here. I want you to circle which of these choices is going to be the graph of the derivative based on all the stuff we just talked about. Okay, same thing for 3 and same thing for 4. Now, if you're not really pausing the video and trying on your own, you're not going to get as much out of it. Even if you pick the wrong answer, you will get more out of it if you try it on your own first. So for all 3 of those, try it. Okay, so hopefully you took a second to try those on your own. Number 2, the first one on this page. If I just look at it in terms of a facing up parabola, that's fine here because this actually is a parabola. And if you just went along the lines of what I was saying before, like, hey, if I have a degree of 2, like this is just a parabola with, x squared. It's like minus 3 or something like that. But then the derivative is just going to be a line. And if you picked this, you are correct. Now, it has to fit everything else as well. So what I mean by that is if the function is decreasing over these x values, then the derivative has to be below the x-axis over those x values. If the function has a turning point, a place where the derivative is 0, then the derivative better be at the x-axis where y equals 0. Then the function starts to increase, which means positive slopes, so the derivative needs to be above the x-axis. It fits all of those things I was talking about. Now, going into the next one. If you thought, oh, this is a parabola, I got to pick the line. That would be wrong. This is not a parabola. They zoomed in on it enough to make it kind of look like a parabola, but it is not. It is not symmetric. If I say it's not symmetric, hopefully everybody's looking at it like, yeah, that's not symmetric. So that is not going to be the line. I'm not looking at this choice right here. That I can actually cross off. It's not going to be that one. Some of the things I need to pay attention to. Where should this guy hit the x-axis? Well, if this is where the slope is 0, that's at negative 1, 2, 3, assuming this scale goes by 1. Yes, it does. So at negative 3, this should be hitting the x-axis. That actually gives me my answer. This is going to be my answer because that's the only one of these 6 pictures that actually hits the x-axis there. But it has to follow everything else. This portion of it is decreasing. That needs to be reflected in the derivative in that it's below the x-axis over that same interval. This portion of the graph is increasing. That needs to be reflected on the graph of the derivative and being above the x-axis. So it fits everything that we talked about. Okay, the last one for this page. Okay, this guy. This is not an x cubed. Okay, this is not an x cubed. So if you were looking at it as though it was an x cubed, you'd be looking for a parabola and you'd pick the parabola, but that's not the case here. There are 2 places where the derivative, silence that. There are 2 places where the derivative is 0. One of them I already kind of did a little tangent line in there. So I'm looking for the derivative to hit the x-axis in those 2 spots, negative 2 and positive 2. That actually narrows it down. So sometimes like you can just look at one fact to get the answer. That is actually my derivative, okay? Let's talk about the other pieces of information. When the function over here that I'm highlighting in yellow is decreasing, the derivative is below the x-axis. When the function is increasing, the derivative is above the x-axis. When the function is decreasing, again, the derivative is below the x-axis again. The function we're working with in this one is like a sine graph. It's got some sort of stretch on it, and you can see that the derivative is a cosine graph with a stretch on it, which, bringing it back to what we talked about, the derivative of sine is cosine. Okay. Fine, I don't even think, oh. Okay, we're going to make a little chart here to summarize. when the function, that's the left-hand column, has a turning point, wrong thing. The derivative has an x-intercept. At any turning point, the derivative is 0, so it has to be at the x-axis. When the turning point has a, oh, I said that wrong, sorry. When the function has a horizontal point of inflection, so this is an example we did not get to see. I'm going to draw a little picture above. If I have that going on my function, the horizontal point of inflection is right there. If I were to draw a tangent line in there, the slope is 0. Okay, so you're like, well, it's just going to have an x-intercept. Well, it's going to be a little bit different because if this is my function, my derivative is going to be, these are all positive slopes. These are all positive slopes. So it's above the x-axis. Then wherever that horizontal point of inflection is, then it's at the x-axis. But instead of this decreasing, like a turning point would change from increasing to decreasing or vice versa, this stays increasing then. These values over here, the slopes over here are still positive. So this is going to go back up. So when the original has a horizontal point of inflection, what's that going to look like on the graph of the derivative? It's going to be tangent to the x-axis there. Okay, it's going to be tangent to the x-axis there. Oops. Okay. Increasing. When the function is increasing, the derivative should be above the x-axis, positive. When the function is decreasing, the derivative should be negative, below the x-axis. My answer key for the notes will be posted in Google Classrooms. You can read it all. It'll be much neater than it is obviously on here. Okay, so the next part. If the derivative is a polynomial of degree n minus 1, then the derivative was a polynomial of degree n. Okay, I'm just going to say what would go here. Polynomial degree n. If the derivative has a positive leading term, this guy's going to have a positive leading term. If the derivative has a negative leading term, the function's going to have a negative leading term. Okay? I feel like you can get all that from the packet, so instead, what I'm going to do that might be of some use is just kind of give you a few examples. So I'm just coming up here into some space. If I have a derivative or a function that's, we'll do real basic, 3x to the third, okay? My derivative is going to be 9x squared. So there's no way this is going to change. We're talking about polynomial functions. Polynomial functions have positive exponents. So if this guy's positive, and I know my exponent's going to be positive, then there's no way for the sign of that leading term to change when I take a derivative using the power rule. So if this guy's a positive x cubed, the derivative's going to be a positive x squared. If the function is negative 5x to the third, and my derivative is going to end up being negative 15x squared. Okay, so I had a negative x cubed, and now I have a negative x squared for my derivative. Okay, the leading terms are going to be the same. They're not going to change when I do the power rule. Okay, last part of this. Corner, cusp, discontinuity, vertical tangent. These are the 4 places where the derivative does not exist. This will be a huge topic next year. I mean, we'll talk about it this year. All the graphs of derivatives and stuff are on the AP Calc exam. I'm going to put D and E. You know what that means? Another way of saying it is, and you'll see this word sometimes, not differentiable. So it's spelled exactly how it sounds, differentiable. So if something is differentiable, it means you can take a derivative. You take a derivative at that place, you get a number like 0 or 5 or negative a million or 1/5, whatever. You get an answer. If you can't take a derivative at that point, it's not differentiable there. The derivative does not exist. Okay, so let's talk about that again. This is me like going off to the sideboard. Like if I was in class right now, this is like, okay, I'm going off to the sideboard. Okay, let's talk about like the absolute value graph. That is a corner. Okay. So I'm telling you, the derivative does not exist right there. So what does the derivative graph look like? Doesn't mean the whole graph doesn't exist. It just means at that one point where the corner is, it doesn't exist. Well, these slopes are negative, specifically -1. Okay, the slope of that portion of the graph is -1. So down here, notice I drew an open circle. It looks like that. And then the other portion of the absolute value graph, this half, it has a slope of +1. So you'll see that the derivative exists everywhere else except for where that corner is. Okay, how is that reflected in the graph of the derivative? By an open circle. In other aspects, you could have an asymptote there, or a single open circle. Just you don't have a value in the derivative there. A cusp. It's made it look like a bird, but that's the general idea of what a cusp is. It's very similar to a corner, just isn't necessarily straight lines. A discontinuity. So if I have a graph that has, a hole in it or an asymptote in it, okay, you can draw the graph for the derivative everywhere else. You can draw the graph of the derivative here and here, just not there because the derivative doesn't exist there. You can draw the slope for here and here, just not there because the function doesn't exist there. So when we're talking about, like, if you draw on a tangent line there, what's the slope? It doesn't make sense to draw on a tangent line where there is no function, okay? So you can still have the graph for the derivative for this piece and this piece. You're just not going to see anything at the y-axis because there's no graph there. Vertical tangent is probably the hardest one. The only example I feel like you guys would be familiar with at this point is this half circle guy. We did a bunch of these at the beginning of the year, like domain, range, increasing, decreasing, blah, 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 all that stuff. Okay, so if I'm talking about the derivative of this graph, if I were to draw on a tangent line here and here, those are called vertical tangents because in order for me to draw a tangent line in at that point, it would have to be a vertical line. So that's a vertical tangent, in which case the derivative doesn't exist because the slope of that line is undefined. If this is going a little over your head, that's okay. We'll see more examples, but I'm still going to talk about it. So if you saw me draw a horizontal tangent, not a great one, just like not that long ago. Well, a horizontal tangent looks like this. Okay, so at this point, this one that I just drew, by the way, is totally fine. Like this is what I drew in that example above. Right there, slope of the tangent line is 0. No problem. But if this looks like that instead, like pretend I took my screen and just turned it sideways, then that point is considered, it would have, if I were to try and draw in a tangent line right there, it would be vertical. Okay, so there's a place where the derivative doesn't exist. Okay, that's a lot. It's hard. It's hard for me to gauge where everybody is, not being able to see you face to face. But you know, we'll do what we can. I'm going to spend more time. Oh, there we go. I'm going to spend more time on these graphs of derivatives. And I have a couple other worksheets and stuff like that we will do to extend on it. But for right now, let's just see how we're doing with what we've been given so far, okay? With this video, we'll see how we did. I want you guys to try this whole second, section of it. And then I'm going to pause it. You guys try it and then come back and we'll compare again. Okay, so I'm going one at a time here. These are the answers for this. So like if I'm just looking at, I'll take one of them randomly. If I'm looking at f, the question is, what's the derivative going to be there? If I draw in a tangent line there, is it going to be positive? Is it going to be negative? Or is it going to be 0? And in this case, it was 0. That is a horizontal tangent. If I draw in a tangent line, it will be 0. K is over here. If I draw in a tangent line, it will be positive. C is over here. Don't be thrown by the fact that C is actually like at the x-axis from what it looks like. You're looking at what a tangent line drawn in would have, positive, negative, or 0 slope. And at C, it would be negative. What's the smallest possible degree of f prime of x? Does it have a positive or negative leading term? So if this picture given is f of x, then this guy would have a degree of 1, 2, 3, 4, 5, 6. So it's got to be at least a degree of 6, but then it's got to be at least a degree of 7 because it's odd. So if this guy has to be at least a degree of 7, then the degree of f of x would have to be, the smallest possible degree would be 6. Okay? And it would have to be positive because if this guy's positive, then the derivative has to be positive based on what I talked about just a couple minutes ago. Describe the graph of f prime of x at f. Oh, I already did that. Right here. Oh, no, I didn't. Okay. So in the picture of f of x, we have one of these, which I did talk about earlier. That is a horizontal point of inflection. So if I refer to the table and the little discussion that I did right at the beginning of this page, if you have a horizontal point of inflection, the graph of the derivative is going to be tangent to the x-axis. If I were to graph the derivative there, it would be like bounce off the x-axis because these slopes are positive, so it's above, then it has a slope of 0, so it's at the x-axis, then it goes above again. It's like boop. Okay, pausing to do the rest of them. Okay, I'm talking my way through this one. This is the derivative. Okay, so now we're going backwards. This is usually where students have the hardest time, is going backwards. I'm given the picture of the derivative. Okay, I gotta switch gears here. So if this is the picture of the derivative, this is telling me what the slopes on the original f of x are. So f of x, I started it, is decreasing. F of x is decreasing from negative infinity to negative 3, negative 1 to 2, and 5 to infinity. How do I know that? Well, I'm just connecting it with wherever the derivative is below the x-axis. Wherever the derivative is below the x-axis is telling me that the original function is decreasing there, has a negative slope. So where is the function increasing? Well, it's increasing from negative 3 to negative 1 and from 2 to 5. How do I know that? Because if the derivative is above the x-axis, then that means the function must be increasing. Okay, so what do I know about the x-intercepts? Well, all of those clearly cut through the x-axis, so they're all turning points. I don't have any horizontal points of inflection, but I can be more specific. Like, not only do I know all 4 of those are turning points, I know that 2 of them are minimums. So I know that f of x has a minimum at x equals -3 and x equals 2. How do I know there's going to be a minimum there and there? Here's how I know. If the derivative goes from below to above, then that means the function goes from decreasing to increasing. When I say goes from, I'm talking left to right. You read a graph left to right. I know that the original function is going to have a maximum at x equals, by the way, these are like local maximums, x equals -1 and x equals 5. How do I know that those guys are going to turn into, on the original function, maximums? Because when I go left to right, this is telling me positive slopes, positive slopes. This is telling me negative slopes, negative slopes. Okay. Number 3, I actually, again, number 2, if that's over your head at this point, that's okay. I'm just like one of those things I'm just gonna have to keep bringing up over and over and over again, and I will. Number 3, I actually drew this when I was just doing the talk off to the side. So you guys can go ahead and like redraw that and then check with my answer key. Okay. Try homework 9. I think homework 9 is actually easy compared to the notes. But I will be around for questions. Definitely planning on doing a Google Meet for this topic and spending more than one day. I'm not moving on to day 10 right away. All right, bye.